Right, good morning, ladies and gentlemen, and I say good morning to people here in Onrus Manor in adjacent to Hermanus. So thanks for joining us, and thanks for those who came to the breakfast. And also good morning to people online, and I see we have some fairly serious geologists, structural geologists participating as well. So we look forward to your discussion. So just briefly to introduce Gerrie van Aswegen. Some of you or many of you will know him. He now lives in Gansbaai, around the corner from Hermanus, still active. Gerrie was born in the Free State in Bloemfontein. He studied, well, he went to Grey College, special school. And then he did a degree and his PhD at the University of the Orange Free State. He's a very well-known and successful mine seismologist, structural geologist. He's had wonderful experiences in particularly the gold mining sector, but other parts of sort of deep mining and underground mining and surface geology. And he worked with some of the best that I think South Africa has produced in that field. And I know one of them was Dave Ortlip, who was a wonderful fellow, and I think Gerrie will probably make reference to that today. He's now retired, but still quite busy, and he also still has an active role, I think, as a consultant with the sort of group across in Stellenbosch Institute of Mine Seismology, and I suspect Gerrie will also give us a bit of background on that as well. So over to you, Gerrie, and thanks for coming through, and we look forward to your presentation.
Thanks, John. I was a geologist, and I became a kind of a rock mechanic. Although they don't like to be called rock mechanics, it's geotechnical engineer is the word. But in our world, it's rock mechanics. But more in the dynamic part of rock mechanics, trying to understand how the rocks break. That brings me to all the fractures. So I've been working on these fractures for many years on the mines, and now that I'm retired, I'm starting to look at these fractures around the place where we stay, and I see things, and I wonder about it, and I'm not sure what I'm seeing, but I'm going to show you anyway. The topic is shears, faults, and fractures, and some learnings from our mines. I probably won't get to the faults. I have a whole section on faults, which we probably won't have time for. I'm going to talk about stress and stress trajectories, which is something we should all be aware of. Just a brief reference to Anderson's fault classification. Simple shear in a ductile domain, that's easy to understand. In the brittle domain, simple shear is a bit more tricky. That leads us to extension fractures and shears. Ortlip shears, explaining some particular important fracture patterns in the mines. And that takes us to curved extension fractures. And now I'm starting to look for curved extension fractures in the natural environment. And that's difficult, but I will tell you what I saw. So that's typical plan view of some mapping done to show the distribution of stress over a particular area. This is stress around an opening. This is the kind of thing that we deal with in the mines. If we think in terms of vertical stress, you make a hole in the ground like a tunnel. The stress, sigma 1, flows around the opening like that. There, the stress is concentrated in the pillar, so the pillar becomes highly stressed. And then we get these things, stress maps of the world. I really don't understand what they mean. What it means, what it shows is the maximum horizontal stress at any given point. But if you are in this environment, obviously the maximum horizontal stress will be some direction, but it has no significance about stress, really. It's the dominant stress is vertical. And it just so happens that the fault thing wants to go that way. So I'm not always so sure, like there's a particular measurement, the taste quint point, which occurs on all the stress maps. But when I look at what I see and what's been published, I see some normal faulting. So I was wondering well, what is it now? Is it not simply isostatic rebound and the wood is pulling apart a bit? And where is the stress coming from? I'm not so sure about that. Simple shear in a ductile lagoon is easy to understand. It's common. We see it all the time. This is the standard thing in the mobile belts in high-grade metamorphic rocks. There we have a granite with large phenocrysts, relatively large phenocrysts, and it's smeared into a banded gneiss. And if you don't see that, you may not necessarily recognize it as a granite. But in the brittle environment, it's not so easy. The brittle domain rock doesn't want to, it wants to crack. It doesn't want to smear like we saw in the previous slide. So this is the environment for extension fractures. Here we look at transpressional and transtensional brittle shearing. So we have a simple shear couple, but in one case, pure simple shear. In that case, simple shear with a bit of loading, normal to the shear box. Another case, simple shear with a bit of unloading. And what you see from this is a different orientation of that E. That's the E, that's a direction along which a fracture would develop, an extension fracture. Always the extension fracture contains the sigma 1 and sigma 2 plane at the time of failure. It's very important. We tend to look at stress indicators in the field and we think it must be old because geologists always think everything is old. But it's not always old. Some of the stresses we see are like in the mines are very, very, very new. Okay. And there's just more. This was published by Ramsey in 1833, pictures from his book. And there we have a simple elastic stress model showing how the stress trajectories deviate through a shear zone, all elastic. This is not plastic flow. This is all elastic. So if I have a fracture developed along the sigma 1, sigma 2 plane, it will curve. That's the important message here. Rock deforms in shear because it's easy. It likes to deform in shear. It doesn't change shape, doesn't change volume. Okay, but it fails in tension. Rock is very weak in tension. You try to pull it apart, it breaks easily. Try to compress it is very difficult. Shear, it's difficult, but the tensional failure is easy. And I'll show you where that goes in. Extension fracture is dynamic. I will come back to that in a second. Where slip rate in an earthquake is maybe 2 or 3 meters per second, the slip rate, the rock moving, the rupture propagation is of a different order, close to the Rayleigh wave speed, 1,000 to 3,000 meters per second. That's the rate of rupture propagation. Very different from slip rate. Stress is transient. It's not permanent. Small changes in strain changes the stress. So you don't only have to change the strain a little bit and the stress is different. Also, because rock is not perfectly elastic, rock is a funny thing. It sometimes behaves elastically, sometimes behaves ductile in a plastic manner. If it wasn't for the elastic properties, we would not have had the earthquakes. So if we could switch off the elastic property of rock, we would not have earthquakes. Relaxation time, because of the rock is not perfectly elastic, there are defects, it deforms under load, it relaxes over time, and we can measure the relaxation time, and the relaxation time is tens or hundreds of years, not millions of years. So the stress of 200 million years ago is gone. It's not here anymore. Finish and clock. Extension fractures, I like this phrase. Extension fractures are fossil traces of stress trajectories. There was a time when there was stress, and the rock fractured along sigma 2, sigma 3. That's permanently in the rock. You can go back and see what the orientation of stress was at that time when the fracture happened. Okay. So we talk about statics, kinematics, and dynamics. As geologists mainly live in this area, we just observe what we see. The rock is static, sitting there. Kinematics is about motion. The units are meters per second. And we geologists look at kinematic indicators telling us in which direction the rock moved, slipped. Slip rates in earthquakes are generally slow, 2 meters per second. And creep rates are of the order of millimeters to centimeters per year. Those are the numbers we're talking about. But dynamics, the measurement is meters per second. It's acceleration. Fracture propagation starts at the velocity of 0 and it ends up at the Rayleigh wave velocity, which can be 2,000 meters per second. So it accelerates. That's dynamics. And it's just the same thing. And okay, I want to go back just one slide. See there, under normal conditions at the end there, under normal conditions, cracks rarely run beyond 50% of the Rayleigh wave speed before they curve and branch. Basically, the rupture runs along this rupture plane, and then it gets a speed wobble when it gets to around the Rayleigh wave, and then it breaks up into subsets of fractures like that. And that gives you perfect, beautiful markings on the fractures, and you know this is a dynamic extension fracture. There's a good, nice example of that there. Extension fractures evolve dynamically. There was, I came across this, the guys discovered this dome that was exfoliating, and the exfoliation happened in steps. Okay. You see, the exfoliation didn't just evolve over time. It popped up. It's dynamic. Okay. So now we can look at the geometries of these extension fractures. First of all, in echelon extension fractures. We know that story. This is Iceland. Iceland is in the news these days. There's some extension fractures on the macro scale. There you can see in echelon extension fractures. On the macro scale, that's 500 meters. You can see that's the North American plate drifting apart from the Eurasian plate. And you look at the geometry, it's very much similar to this picture from Ramsey. In fact, in this case, it's not purely extensional, it's extensional plus it's a transtensional shearing to give you that particular pattern of extension fractures. Now I have to talk about the Ortlieb shears. I can talk 2 hours about them, but I'll try to be brief. This is a classic Ortlieb shear. It's a dynamic brittle shear that occurs during mining under very high stress conditions, and the new fault evolves, and you're going to get a magnitude 3 about as a result of that. Displacements up to 10 centimeters. Very interesting stuff. But the important thing about them, you see here, you see breakthrough rupture to allow displacement of centimeters, but you also see this very intense n-echelon set of extension fractures. Dave and I went underground. This is many years ago. There was a big bump at Mponeng mine, and we found this shear at the end of a gully. And the trick is to understand what we're looking at. That's the gully. Here's the footwall. That's the stope over there. There's a gully in the stope. There's the wall of the gully, which broke off along the shear zone. So it dips towards me as I stand there. And you see this very, very strong linear fabric on the edge of the shear zone. Now, this is one of the characteristics when Dave described these Ortlieb shears in detail. He spoke, or he wrote about it many, many times, and he never knew what to call it. He had different names for it, and I eventually said, this is an Ortlieb shear, and I wrote a paper on that, and now it's an Ortlieb shear. At least now we know it. So we got to this, and he was very happy, and he showed me this lineation. You see, this is typical of these shears. And then we were lucky that we could revisit the site after they advanced the gully, so we could now see the whole shear in detail. And this particular one is very interesting because there's no breakthrough shear rupture. The displacement here is infinitesimal. maybe a millimeter. There's no 10 centimeters displacement. It's an all-clip shear, but there's no significant displacement. It can only happen in a very stiff environment. And I don't want to go into stiff systems and soft systems. That's a whole topic on its own. But in a very stiff environment, you can have this phenomenon. And you see this all-clip shear, and you see these extension fractures, and there's no absolute doubt that this is a dynamic extension fracture. There's no doubt about it. But it looks as if it's folded, but it's not. It's following the sigma 1 trajectory. This is what it's doing. So the extension fracture followed the stress, and it obtained this shape. There's the explanation. There's a shear zone, there's the extension, the sigma 1, and it goes through there. So this is a very important photograph, which I've looked at many times. That leads us to this story. This is a classic picture of fractures around stopes in gold mines. It's been published like in early 80s. And it's in every textbook you will find it. The one thing, it's all described, there's bedding, there's shearing, there's this and that, but this particular set of low angle extension fractures were never properly explained. Ryder and Jager and Ryder tried. They have some story about shallow dipping fractures over previously hard patches and what. I don't buy that. A better explanation is simply put a shear couple in there, and all of a sudden it's explained. It's very simple, very easy. So that led us to delve into this a bit more. And we said, okay, well, now let's see what happens. This is the stope. There's the stresses, and the stresses around the front of the stope, of course, are very high. This is 2.5 kilometers below surface, very high stress. So you have these extension fractures which form a head of the face. Now, for some reason, there's a spacing, about 2 meters spacing, which is a bit more than the 1 meter advance. There's a bit of not so clear why we have, in this case, a 2 meter spacing of the extension fractures. There's a long story about that, but that's where the extension fracture happens. I call it E1. That's the first extension fracture. Now the stope advances, and another one happens ahead of the first one. Okay? And immediately you have a shear couple. Once you have these two discontinuities, you have a shear couple. And the shear couple is such that this side wants to go down because it wants to go into the stope, and that side stays behind. Immediately you have a shear couple, and you have these extension fractures. In this particular case, because of the stress orientation, it is transpressional. There's a shear couple with stress normal to it. So the extension fractures make a large angle to the shear zone. Okay. Then we advance the stope again, and now this set of extension fractures end up in the hanging wall above the stope, where the stress is completely different. Here we have this set of E2s. Those are the E1s, these are the E2s. And now we have this stope below us, and some shearing takes place along the E2s. But now it's transtensional, because there's a hole below you. The rock wants to actually fall into the stope. So this is now transtensional shearing, and now the extension fractures have that shape. And there you see them. These are the E1s, they are the E2s, and there are E3s. These are beautiful things to see. I mean, this is amazing stuff. To see these transtensional extension fractures in the hanging wall of the stope. So we've got extension fractures which rotate following the stress field. Let's look at some pillar failure in the class top. This is a nice example of a pillar failure. The way the anchors were pulled as the rock mass was ejected points back to the origin of this seismic event. Okay, because these anchors were radiating from this point. So we can go back and say, okay, the source must have been there. We look in section, we see that's the mechanism. This part of the rock mass wants to go out, Along a bedding plane, there's some normal shear, and we see these extension fractures, which are curving. Okay. Now we go to Tumela. There's a platinum mine, pillar burst there. This is some kind of bedding. There's the pillar which burst, and there are the extension fractures. Look how they are curved. And here I can prove to you the direction of slope by looking at the way this anchor is bent. Okay, so clearly it is the slip is as normal slip as indicated, and the extension fractures are doing exactly the opposite as a ductile fabric, as a ductile schistosity would do, exactly the opposite. El Teniente mine in Chile, we had a burst there. Many 100 meters of the tunnel was really badly damaged. We sorted out the mechanisms by looking at the moment tensor, and we eventually understood that this was the mechanism of failure. And you see in this part of the sidewall, because of this dynamic closure, you have this kind of buckling failure. And on that side, there were pre-existing discontinuities. You have this kind of shear failure. And then between two of those, in between two pre-existing discontinuities, there's no bedding here. This is igneous rock. This is tonalite or something. We have this formation of these bands, these rotated extension fractures. There's only one explanation. In this case, it has to be extension fractures which curve according to this stress orientation in this shear zone, which then happens dynamically, form dynamic. Another observation. Looks like cross bedding, but it's not. This is in quartzites below the basal reef at Tautona mine. You can see the fabric asymptotically approaches both the hanging wall, the above and below the layer. It's not cross bedding. Okay, this is a beautiful cross bedding at the plot. So the explanation is again that one. It's E3 type extension fractures following. See that this rock mass wants to move into the stope, so it moves like that. So it's transtensional, and that's why it forms that particular shape. So that's the explanation. Do they occur in nature? And this is where the fun starts. This is I call it the Raaswater shear zone, because it's right where we stay. I stay in Raaswater Street. It's just down 100 meters from my house, looking towards Hermanus. That's now standing at Hermanus, looking towards Gansbaai. You see very similar intense fracturing. And I've tried to understand what the relationship is between the orientations of these fractures and the bedding and the layering and folding. So this is different Google Earth shots. This is from Hermanus area. You will probably recognize them. You see it's always northwest, southeast, sometimes a bit steep towards north and sometimes towards east. This is now at the site of the Klipgat caves, and this is at the site of the Drupkelder caves. And now in this case, because I can actually see it, I with red I indicated the strike of the sandstones, the TMS, the fold axes basically. And there's the trends of these extension fractures. That's at Raaswater. This is at Stanford's Cove. And I'll come back to this picture, very important one. This is at Kleinbaai. This is further along the coast. The place is called Soetant something. You can see the orientation of the extension fractures and the orientation of the bedding. You can see actually a nice fold there in the bedding. This is at Buffeljachts. Extension fractures like that, trend 167. That's the bedding. At Quinn Point, there is the folding of the sandstones, and that's the orientation of the extension fractures. I have a bit of a suspicion that this was observed at the time when they decided to have a point to put on the map for the stress orientation in this part of the world. This is a conjugate set of structures in the mountain behind Gansbaai. And this is, so we're talking about a bit of scaling variance here. This is the Kleinbaai. See these very similar pattern of extension fractures, Kleinbaai. Just 1 meter further, you can see that these extension fractures have a tendency to rotate. They're not so straight anymore. They bend. This is me trying to explain to a bunch of OGG guys what's going on there. No one had any idea what I'm talking about. That's the picture. That's the extension fractures. All brittle. I mean, the bedding is subvertical here. So there's no bending that can bend fold. This is fracturing, and the fracturing is doing that. It's very similar to the picture I took in Chile, in the mine there. This is at Raaswater. That's the bedding, that's the extension fracture. This is one particular site, and I'll show you some fractures here. That's the main fracture. You can see it there, over there, the main fracture set. There's a subset of that orientation. There's another subset. So between two sets of fractures, between two fractures, you have a shear couple, and more extension fractures evolve. And there's another one. So this here we have some scaling variance effect, but each time between two discontinuities, there's shear displacement and extension fractures, in echelon extension fractures happening. And of course, you can see that at this very same site. This is an interesting fact that across the gully, this is bedding, vertical, very steeply dipping bedding, and there's a shale band or something that's eroded away. And on the other side of this weakness, the orientation of the, or either orientation changed or another part, the other set of the conjugate set is dominant. So on this side, the structures strike like that, and on that side, and it all happens across this weakness. At Stanford Scope, now that's all extension fractures which are relatively late in the Cape origin. At Stanford Scope, we have this zone of very intense ductile fabric. This is the TMS on its head, vertical. There's a fault over there on that side, as my friend here will recall, it's subhorizontal. So there's a very distinct fault. That's the trend of the extension fractures on the one side of the zone, and that's it. They changed by 10 degrees. But now we've got something else. In this shear zone, which is in this basically the core of a fold, this is like intense actual planar folding, we have some brittle layers, and they show the same phenomenon. So these are the extension fractures which are old as part of the Cape fold, or late part of the Cape fold process. Over there, that part there is the new ones. It's called the Raaswater shears. And there you can see a nice fractographic pattern proving that it's actually an extension fracture. I'm still looking on. I think I found one in one of these fractures, a fractographic striation, which suggests, or which would prove that it is actually extension fracture. So, wherever I look, I see it. Now back at Raaswater now, so remember this is now That lot there is the general extension fractures, and this is the bedding schistosity in a core of a fold in the Cape Fold Belt. So we're looking at a different kind of extension fractures here, and this is right there as well. This is now back at Raaswater, looking to the north, northwest along the strike of the TMS, and you can see there's another one of these very clear set of extension fractures in the sandstone because it's bounded. The two layers have moved relative to each other in the elastic environment. So curving extension fractures reflect curving stress trajectories at the moment of failure. It can be confused with ductile fabric or even cross-bedding, so one must be careful. And it's possibly quite common in the natural brittle environments and maybe has not been recognized in the past. I'd like just to show some 3D models. Stop share that. And then I share again.
Okay, I want to have a look at this Raaswater shear zone in a bit more detail. This is a drone image of the shear zone. We have the TMS layer dipping steeply towards the southeast. There's a weathering layer, shale band I guess. I couldn't find the outcrop, so I don't know what it is, but it must be shale. And another layer, and maybe some interesting layering inside there. Here we see, look at the extension fractures across here, very intensely developed, and there's also a change in the orientation across this band of weakness. We're going to have a look at that, and I'm also going to have a look at the 3D model in this area looking towards the southeast. So this is the same area but shown in a 3D model. You can see the steeply dipping TMS layers there. This layering is dipping, I guess, at around 70 degrees towards the southeast, and this lot here, so this wall of the gully is the sandstone bedding. This wall is shallower dipping, and in fact it's a set of extension fractures developed between these layers, and that actually creates the slope of the wall. The orientation of the extension fractures either side of this gully or this band of weakness are different. We can look at them like that. Make sure they're here. Oh, I can't get them. So we can look at the orientations of the extension fractures on either side of this gully in a bit more detail. You can see the one set. That's the set at the southeastern side of the gully, has that orientation, and the other set has that orientation. So it looks like the extension fractures on the south side of the gully are dominated by the one conjugate set, one part of the conjugate set, and the other conjugate set dominates the other side of the gully. Why that is the case is unclear, and I'll have to try and think about that. Now I want to just have a look at this part, look at the 3D model of this part looking towards the southeast. So this is the shear zone. We can see intense shearing, fracturing, brittle fracturing in this area here. You see some en-echelon fractures on that side. And see these curving structures, curving extension fractures. Looks like a characteristic of the Raaswater shear zone. I try to answer some questions here, comments. This one comment about what these orthotype shears should really be called, simply en-echelon fractures. Yeah, but technically orthotype shears are dynamic brittle shears. They are unique to the mining environment where the local stress is very high and the system relatively soft. That is why they can show shear displacements of up to 10 centimeters for a seismic event of magnitude 2. This high stress soft loading system is not readily found in nature. Where they do occur far ahead of the mining phase in the mines, the loading system is sufficiently stiff to prevent the breakthrough shear ruptures, and the result is the orthotype shear with infinitesimal shear displacement as shown in slides 30 to 32. The nomenclature of the orthotype shears has a long history, and I guess the best way is to just read up on it, and there's an easy way of reading on about these in this paper, and you can just Google it and you'll find it easily, and it's freely available. Is the fracture mechanics more about the speed wobbles? A simple way to think about it is that as the rupture keeps accelerating, the energy at the fracture tip line becomes too much and the rock decides to split into numerous subsurfaces or sub-fractures to spread the load and allow sufficient dissipation of the energy such that the continuation of the growth is actually inhibited. Age of the Raaswater brittle shears. She knows the geology very well. The question refers to the younger formations, but the Stope group. At the type locality of the Raaswater shears, an unconformably overlying 10 meter of brittle limestone dolomite does not show any of these fractures. So the answer is the fractures are young relative to the Cape folding, but old relative to the Stope rocks. It doesn't mean that there are not some younger structures in the Stope rocks, but at the type locality, these fractures do not go through into the younger rocks. Safety of the nucleus site for nucleosite. An interesting thesis showing how, with minimal information, geologists can come up with major conclusions. The Bermudas fault, main topic of research of this thesis by Matthew Hodge, that Bermudas fault does not outcrop at all, requiring detailed documentation of the tilting of the bedding, cross-bedding over the cover in the cover rocks to estimate the fault displacements. So there are younger structures, and the younger Stope rocks are affected. So, but in this particular case, the eventual estimate of the earthquake hazard along the Bermudas fault, I think, is overly pessimistic. The stratigraphy of the unit of shale at Stanford's Cove. I do not know the TMS stratigraphy at all, but Mike Dormus did show me a significant shale band just east of Kleinbaai. Kleinbaai is just over there, and I believe it is the same unit exposed in the core of the anticline structure at Stanford's Cove. High stress affect the stope face when you allow caving of the back area. This is a rock engineering question. In principle, the more you allow the stope to close, the higher the stress at the face. But when the collapse of the back area allows displacements along bedding planes above and below the stope, perhaps the high stress could be pushed further ahead of the face. I was never involved in such studies and simply do not know the answer. When Henry asked about this question, I did not quite catch his drift, and I went rambling on about stress being a function of strength. For a given general load, the stronger rocks, pockets of rock, will be more highly stressed. Not because pockets of stress remained after historic tectonic loads, the presence of a fault could alter the stress orientation, and the local stress anomaly could result, not because of the ancient tectonic load which caused the fault, but because of the different response of the rock to of the rock mass with the weakness in it to the current load, mainly gravitational in the case of our mines. Why do we find gold in the Wits but not in the other stratigraphic units like the Transvaal group? Now, there's a long story. South Africa is really blessed with world-class mineral deposits, and some of them are very unique. In the specific case of the Wits, the conditions were very specific, high rainfall, zero vegetation, the chemistry of the atmosphere, no oxygen, everything was just right, and those particular conditions were never repeated in history. John will gladly point you to a talk on this subject in the OUG repository of Zoom presentations.
And I mean, if you speak to a lot of the geologists in this room and on the, on the talk, these amazing deposits that we have in this country, the Wits Gold and the Bushveld complex, are really, geological anomalies. There's various processes that come together and give you these, in our case, these mega large deposits of minerals. The Bushveld is a classic, and the Wits Gold is another, exceptional anomaly. And they happen sort of once in a while, where all the circumstances sort of work together.
Gerrie, you mentioned there where the stresses are relieved. They are completely relieved within that stressed area, and you have then E3 fault forming.
No, I'm not saying stress is not released. When you push, or you create this shear zone, so you've got this couple, and then this extension fractures evolve, and you have infinitesimal strain, very small strain, millimeter scale. The stresses are in a very small way less. You don't really, you never get rid of stress. Stress is, you can push it here, you can push it there, but you can never get rid of stress.
Does the competency of that rock then change?
Absolutely. Well, once it fails, that zone is weaker.
So your stope mining is then dangerous in that area.
Well, in this particular case, this low angle structures fall on your head. I mean, the hangwall falls on your head. It's a very difficult environment to keep up, because you have to, all these slabs are in the hangwall, and then the face bumps, and then everything comes down. It's a massive problem. So the support costs are very high.
Yeah, Gerrie, I've got both a comment and a question. I don't think we realize just how important structure, faults, fractures are. But if you take just here Greater Hermanus as an example, we get, and it's growing, we get about 35% of our fresh water, potable water, from the underground aquifers, particularly highly fractured rocks at the base of these TMS mountains. That aquifer is held in very fractured rock. If you drive up the valley, Emelanada Valley, you can see some of it in the peninsular formation at the base of the valley. And many of our mineral deposits are, again, fault controlled or fracture controlled. If you look at the manganese deposits here in the Cape, and there's several of them. The best example is here at Caledon, and we went there with Jean. You might want to comment, Jean, to look at it last year. You have a huge fault line and hot springs between the TMS mountains at the back and the Bokkerveld in the front, and you have this, it's not very big, but a huge manganese deposit. And if you go around Clarence Drive, you'll see a little adit, not closer to the Royal side. There's a little manganese adit there, and if you look up the mountain above it, you see a very distinct fracture line, and this adit and little manganese deposit is directly on that. So structure, faults, fractures are extremely important from things like formation of our aquifers. and they're hugely extensive. If you see the Steenbos Valley and the number of boreholes drilled there, again into the TMS, 1,000 meters, and the water that comes out of there was, pumping. And that water is now being used to supplement Cape Town's water supply. So this business of yours is far more important than just understanding fractures. Why in the Wits, obviously, those rock bursts killed people, but it's a very important field if we actually think about it, globally.
Yeah, if you look at these fractures, I can just imagine. I'm pretty sure our aquifer at the Kelders is from these quartz sites with these fractures. Okay, and now unfortunately, it could be this. The nice thing about that, when you see these curvings, it's transtension. And that's good for water because it's opening up. Okay, hopefully it's young enough, so it stayed open. That's the question. Yeah.
Okay, and my last comment goes back to nuclear, and I'm probably a bit of a heretic, but if you look around the world, including our nuclear power station, just next door to Cape Town, nuclear, like it or not, has been probably the safest, the cleanest, the most efficient way of producing electrical energy or energy. And the stats worldwide are amazing. Yes, there was Chernobyl. There was the 3 Mile. And 3 Mile, yeah, there will be a few. And the tsunami, which almost flattened the Japanese nuclear power station. But compared to, say, just coal in this country, the number of people that die every year on the Highveld from ingesting CO2 fumes is staggering. We forget about Coalbrook, where one mine and the collapse of a dolerite sill in a coal mine killed hundreds of people. 300 odd people. So like it or not, if we want clean, efficient base load, we need something like nuclear energy. And as I say, Overberg has been extremely successful. It's had its challenges. And all the time, there are things like an international nuclear agency which keeps an eye on these things. We've probably got a good probability of being well looked after. But, we cannot get away from the fact that reliable baseload energy, particularly in this country today, is absolutely essential. We all rah about going solar and going wind power, but that comes at a huge price and a cost. And it's fine for us, who don't have kids going to school. Go and look at the township when the power's off here at night. It's frightening, and how people get knifed, how many people get knifed and stabbed. So, let's not dismiss nuclear, but it's a wonderful resource and should be used better. Okay, thanks very much, Gerrie. And thanks for coming. And if any of you, we don't have your details, please just give them to us. I've got a piece of paper and we'll put you on the mailing list and we'll gladly send you our links. And all of these talks, just so that you know, and it was for the audience, the Zoom audience too, are all on YouTube. So this talk in a couple of days will be on YouTube. You can go and listen to it again at your leisure. You can play it, replay it, stop it, and that sort of thing. So there's a huge resource. I think this today will be the 122nd presentation that we've given since the start of COVID. And there's some amazing stuff. I mean, Gerrie's and the people he's been associated with are world experts in this field, and we've been very fortunate to have people like this come and talk to us and record them and then put them on YouTube. So there's a wonderful resource there. So thanks, Gerrie, and thanks to everyone else.